Hello students, now we shall continue the same topic, system of particles. In the previous class, we have discussed the relation between angular momentum and as well as the torque. dl by dt equals to tau x1. So this expression we have discussed. According to this, it has been explained that the external torque is equals to rate of change of angular momentum, or reverse. The rate of change of angular momentum is equals to the external torque. So as we have discussed the angular momentum concept, which is as angular momentum is equals to linear momentum into perpendicular distance. The moment of momentum also we can say, that is angular momentum. So whenever the object is set up under the motion, that is any object it is under translational and rotational motion, particularly rotational motion, then angular momentum do exist for that. So that when there is an angular momentum, as we have discussed previously, linear momentum P is equals to mass into velocity. So this is linear momentum, it is mass into velocity. Okay, so that is for any object which is moving along a straight line or linear motion we can say. But if it is a rotational motion, there exists angular momentum. Okay, hence the rate of change of angular momentum is equals to torque we have explained. Now we go for the previous topic where Newton's second law has been explained. That is, force is directly proportional to the dp by dt. Okay, Newton's second law. The rate of change of momentum, linear momentum, it is always directly proportional to the force applied on the body, and the body moves in the direction of force. That is Newton's second law. So in this equation, we have proved F is equals to ma, that is the next one. But here the rate of change of momentum, what has been discussed in the Newton's second law, it is about linear momentum. It means if any body is under motion, or if any body is supposed to get under motion, the force is required to make that body to be set up under the motion, or it has to be stopped. So force is required. So that external force. And the momentum will change. If the body is moving with a certain speed and suddenly if you apply any force, then its momentum will change. Mass is the same, but due to the application of force, velocity will change. So that is the momentum, rate of change of momentum is directly proportional to the applied force. Imagine if you are riding a bicycle with a certain speed. If suddenly, if your friend or anybody else, if they push you with a certain amount of force, mass of cycle and mass of person who is riding will be the same. But due to the application of force, due to the pushing, the bicycle will move little bit faster. Its velocity will increase. So that velocity will increase is nothing but change in the momentum. So that change in the momentum is depends upon the how much force has been applied. So that is Newton's second law. As the force makes change in the momentum. Same concept. Now we are going to explain for the rigid body which are under the rotational motion. Imagine if the fan is rotating. If the fan is rotating with a certain speed, it is depends upon how much voltage we, or we can say that it is based on the regulator, at which number that we usually do. So with respect to that, it will be moving, and it is rotational motion. If suddenly a force is applied, that is we call it as torque, external torque for the rotational motion. Okay, hence whenever the torque is applied on any rigid body, that torque makes the body to rotate, or it will produce a angular motion or rotational motion, even translational motion also. So due to the application of torque, rotational motion do exist for the rigid bodies, so that this torque is nothing but the force. But usually we call torque means force into perpendicular distance. At what point the force is applied for a rotating body. So this torque will change the angular momentum. That force will change the linear momentum. Here the torque changes the angular momentum. Hence, it is quite same as that of the Newton's second law also. It is analog of Newton's second law also we can say. Okay. So this is the previous class explanation. Now the next concept in this class we are going to explain is when there is an rotational motion as well as translational motion. Any type of the motion a rigid body can execute. But do whether all those motions, whether the translational motion and the rotational motion will be under equilibrium. It means will they maintain the same speed of motion, translational or rotational. So that we have to discuss. That is equilibrium. Equilibrium conditions of rotational and translational motion, or we can say that equilibrium conditions of a rigid body. So the concept of equilibrium or the meaning of equilibrium is a rigid body is said to be under equilibrium if there is no change in the translational or rotational motion. There is no change in the translational or rotational motion should take place. That is equilibrium condition. Or the force should not alter, or unless and until the force or the torque is applied, then only the translational or rotational motion should change. If not, the rigid body should not change its translational or rotational motion. Then we say that it is in equilibrium condition. That is translational as well as rotational equilibrium we can say. Okay, that is for translational means a force, the force whenever it is applied, it should not change translational motion, or when the torque is applied, then it should not alter the rotational motion. Then we call it as the body is in equilibrium condition. And in that, like two equilibrium conditions we are discussing. One is translational equilibrium. Translational equilibrium means if any body is under the translational motion, any external forces acting like F1, F2, F3, so on, all the number of forces which are acting on the rigid body which is executing a translational motion. Okay, which is executing the translational motion should maintain the same linear momentum. dp by dt we can say, because external forces acting on the object can change the linear momentum. That is the total external forces. How many external forces are acting on the any object that is rigid body? Like we are calculating the translational equilibrium for if a body is sliding down an inclined plane. So this body will be moving with a certain constant velocity. Then definitely it will be having some constant linear momentum also. So that the external force whatever we apply, it should maintain the constant momentum. That is law of conservation of momentum we can say. Then only we can say it is under translational equilibrium. So that any number of forces it may be acted by the body on the body. All the forces they are called as external forces. Okay, so that like sum of all the forces whenever they act on the body, it is nothing but total forces. So that I can write it is F external sum of all the forces, which is equals to dp by dt, or we can write total external force is equals to d by dt of momentum is mass into velocity. Mass of the body is remains same, so that F external is equals to m into dv by dt we can write now. Now the condition is if F external or the total external forces acting on the body, all the external forces F1, F2, F3 all together we have taken as F, that is total net force we have taken. Hence, if F external is 0, if F external is 0, then dV by dt is equals to 0 we can write, since mass is not equals to 0, so that V is equals to constant. dV by dt is equals to 0 means this concept, velocity of that body is constant, because the constant term, whenever we differentiate, we get to 0. External force acting, if it is 0, which means if the external force does not changes its linear momentum, so that it is moving with a constant velocity, we can write. So this is we call it as translational equilibrium. Even the vice versa also we can do. That is, whenever the F external as it is we write for momentum, or F external is equals to, when I write dP by dt, okay, if F external is 0, dP by dt is equals to 0, since external force acting on the body is 0, so that P is equals to constant, we can write. Linear momentum remains constant. So then we can say that the object is under translational equilibrium, which means if any body which is sliding on the surface, or any object, any rigid body which is showing translational motion, that motion is said to be equilibrium. It means same only when either its velocity should be the constant, with a constant velocity the body should get translational motion, or its linear momentum should be the constant. With a constant linear momentum, the body must move. So that is we call it as translational equilibrium. Similarly, come to the rotational equilibrium. Rotational equilibrium. As we have discussed that the rotational motion exists for the rigid body when the torque acts on it. So that a simple concept, if there are so many number of torques acting on the body which produces rotational motion, which is in terms of dl by dtv, right? Because a torque can execute rotational motion of the body. So that total torque, when I write, it is dl by dt. So the meaning of this expression is the external torque, whenever it is applied, or when the torque is applied on a body, that will produce a rotational motion. But what the equilibrium condition is, the torque should be such that the angular momentum should be constant. Then we can say that it is rotational equilibrium. So this angular momentum should be constant. For that, I should write F external should be 0. If external torque applied is 0, then we can write dl by dt is equals to 0, which means L is constant. So when I am writing external torque is 0 or external force is 0, so which means for any rigid body, the equilibrium of rigid body, which includes translational motion and rotational motion, should not be altered or should not change by the application of either the force, either the torque, so that the rigid body should maintain constant translational equilibrium as well as rotational equilibrium. And the rotational equilibrium and the translational equilibrium means, when we talk about the translational equilibrium, the body should possess either same or constant linear momentum, or it should have constant velocity with which the body is going to be showing translational motion. And in the rotational equilibrium means, as we have derived the condition for the rotational equilibrium, that is external torque must be 0. So it means it is not exactly meaning that the external torque should not be applied. The other meaning is the this angular momentum should be constant such that the external force applied should not affect this rotational motion, or we can say that angular momentum of rotating body. When the torque is applied, then only the rigid body will show the rotational effect. But the torque should be such that all the total number of torques acting on the body should be such that it should not change the angular momentum. It should maintain the constant angular momentum. That is the meaning of rotational equilibrium. Okay. So like this, we can write two conditions. One condition is translational equilibrium. Another condition is rotational equilibrium. Okay, like for example, angular momentum I am talking about. The example for the constant angular momentum is very best example. The sun, the moon is rotating around the sun. Sorry, around the earth, and earth is rotating around the sun. So these two are having the rotational motion. For the earth, the axis is the sun. For the moon, the axis is the earth. Their velocity is remains same, angular velocity. It will not change. Because of that, we can say that for a day to happen, 24 hours is required. For one complete rotation of the earth, 365 days is required. Okay, it is not going to be changed. That is angular velocity or angular momentum, we can say. Likewise, the bodies or rigid bodies should be set up in such a way that any external torque, where the torque is going to be applied on the earth, is nothing but the force between the sun and the earth, or the force between the earth and the moon. That is external forces and the torque going to be applied. Even then, it is maintaining the same angular momentum. So this is the concept of equilibrium condition. It means the bodies, the rigid body should be under the equilibrium condition. Like that, two conditions we have discussed. One is translational equilibrium, another one is rotational equilibrium. So now we shall go for the next one, that is principle of moments. So here the principle of moment is nothing but whenever the force is applied at a perpendicular distance, we say that it is torque is going to be applied. Okay. If it is a rod, I can balance the scale or a duster. When I hold this duster on my finger, definitely it may not be possible me to hold this until and unless I will get a correct position point, the duster where the center of mass is there, so that it can be balanced. Like this, it is going to be balanced. Now, if I apply a force either here, definitely it will fall down. At the same time, even if I apply another amount of force at this end so that it should not fall, then we say that it is principle of moments. Okay, it is just like a seesaw. The children will play in the ground, no seesaw. So like this, they will move up and down. It only happens when the two forces acts on the two edges. That is, we say that principle of moments. If a child sits here, then this seesaw will bend. It will not balance the entire way unless and until one more mass is acting on this point, so that both the forces should act. At a certain point, we get the balance. Hence, torque, force into perpendicular distance, F1 d1 should be equals to F2 d. This we can say. Otherwise, F1 d1 minus F1 due should be 0. Net amount of force or the torque. If a person sits here, if a child sits here, then only one side force is going to be applied, but other end will be moving upward. It will not balance until and unless another force acts on this. It is a simple concept. So this we call it as the principle of moments over here. Like this, based on that, one more concept we have to define, that is center of gravity. Okay, center of gravity. Otherwise, we can say that it is radius of gyration. Also, we can say for any rigid body, irrespective of the shape. Okay, any rigid body, irrespective of the shape. It may be any shape, and irrespective of what type of the motion they show you, whether it is a translational motion, rotational motion, linear motion, whatever it may be. Okay, it is containing so many number of particles in it. It is made up of so many number of particles. Every particle shows its force on the downward. It is due to the equation F is equals to m into g. That is, force is equals to mass into acceleration. That is weight of the body itself. We are writing F is equals to m into g is nothing but weight of the body. So every particle which is made up of, or this entire system is made up of, will be acting towards the gravity irrespective of the shape. Okay, and whenever such objects we consider, whether this is, whether any plane lamina, circular lamina it may be, then also it will act downwards only. But somewhere we can find for the whole entire system which is made up of with different mass objects or mass particles, somewhere in the entire system of this rigid body, a point in the rigid body where the entire weight of the body is supposed to be balanced. That point we call it as center of gravity. Okay, any object, like for this example, again the duster only, entire weight, not the mass. Okay, entire weight of the body is supposed to be concentrated at that point. That is called as center of gravity. Okay, so it is just like when I hold with the two fingers, somewhere at this point, the weight, entire weight of the body is supposed to be concentrated so that it is in equilibrium. That is, this point is called as center of gravity. Okay, and even you can see in the nature also, so many rocks they are standing on each other. Like this, you might have seen so many rocks with a very sharp edge or with a very small contact with another surface, they will be standing, which means they are balancing in such a way that the weight of this rock is concentrated at this point. Hence, it is balancing with the gravity also. Okay, of course, it is maybe miracle, but it is not exactly. The entire weight of the body is concentrated at this point. So this point of this body is, we call it as center of gravity, which means the whole weight of the body at a certain point, it is supposed to be concentrated, it is supposed to be balanced by that point. So that is called as center of gravity. Even sometimes whenever we walk in a mud, if you get slipped or if you get skid, we try to balance ourselves. Whenever we try to balance ourselves, we balance either on our arms, either on the legs or on a finger, somewhere anyhow we try to balance ourselves. So whenever we try to balance ourselves, means at that point our entire weight is going to be concentrated. That is, we call it as center of gravity. So that center of gravity may exist at any point for the rigid body. It is not like only at that certain point it should exist. It may be exist at any point. If it is a rotating body, it is translating body. M1, M2, M3, M4, somewhere it may exist. At this point, center of gravity may exist. Or at this point, the center of gravity may exist. So center of gravity means the entire weight of the body is supposed to be concentrated. That is, we call it as the center of gravity. So what main or important concept of the center of gravity, or what way, in which concept we have to use that? It is again whenever you open the door and close the door. Okay, the couple of forces what we apply, like opening or closing the door. The door will get closer and open, but center of gravity will be somewhere. Even the huge gates also, if you see, at the edge only they will give. So the huge gates, at the edge, the hinges will be there, so that it can be opened and closed very easily. This depends upon application of point of application of force with the axis, at what distance we apply the force, and that very easily the gate can get opened or closed. Okay, it is showing the rotational moment. I'm talking. It is showing the rotational movement. We have studied in the Newton's first law the concept of inertia. The body has two types of the inertia especially. One is inertia of rest or inertia of motion. The meaning of inertia of rest and inertia of motion means unless and until the external force is applied, the inertia of the body will continues to be in its state of rest. That is called as inertia of rest. It will not move unless and until any force is applied to move that body. Or the body is continuing in its state of motion, that is called as inertia of motion, until and unless any force, external force is applied to stop it. That is called as inertia of motion. Okay, if an object, any object like a duster kept on the table, or books kept on the table, or the desk in the classroom, will remain there only stationary, that is under rest, until and unless a external force is applied to displace them. That is, the desk will be having inertia of rest, which means they will be continually in state of rest. That is called as inertia of rest. Okay. Likewise, inertia of motion means the bodies will show continuously under the motion until and unless any force is applied to stop it. That is called as inertia of motion. Similarly, for the rotational motion also, one inertia exists here. That is we call it as moment of inertia. We call it as moment of inertia, where it is denoted by the symbol I. Here also the inertia, but it is not inertia of rest, it is inertia of motion, but it is moment of inertia. How exactly the rotating body starts moving. Okay, example of this one. When I put the hinges at the end, it is very easy to move the object. But at the same time, if I apply the force exactly at this point, near to the axis or near to the wall, the same force will not be possible to open the gate when applied at the near point of the axis. We need to apply more force to open the gate. Though the gate is same, but the point of application of force is different. First point, it is almost outer edge of the gate, so that it is very easily we can open and close. Same amount of force if we apply at the very closer to the wall, then the gate even may not rotate, even may not move also. So that concept, it means very easily whenever it starts moving. So that is nothing but moment of inertia. It comes under the rotational motion, which is defined as, moment of inertia is defined as the product of mass of the body, total mass of the body, and the square of the point of application of force, the square of the distance of the point of application of the force, so that the object should be set up under the motion. This is, we call it as moment of inertia, or we can write I equals to m r square. So capital M may be, since m can be like m1 plus m2 plus m3 and so on plus mn, and r can be r1 plus r2 plus r3 plus r4 like this. So total moment of inertia is defined as product of mass of the object multiplied by, or product of mass of the object and the square of the perpendicular distance from the axis of rotation. Okay, that is nothing but moment of inertia. I equals to m r square we can write. Okay, this is one more important definition, or even we can say the physical quantity of rotating objects or any rigid body under the rotational motion will have moment of inertia. Okay, and this can be understood very easily with an example of gate or a door. Moment of inertia will be very easy. Like mass of the gate is same, but point of application of force is different. As the R is more, moment of inertia is more. It means very easily it will move immediately. If R is less, it is less. Okay, like this the moment of inertia can be understood. So this concept of moment of inertia is explained for the rotating bodies. Now, with respect to this moment of inertia, all other concepts, physical quantities which we have discussed earlier, again we can go back to that same thing. Like torque also we have explained, external force also we have taken M into G, M into A, and based on the rotational motion, the all the objects, how exactly it can be explained. That can be based on the moment of inertia, we can explain. Even the kinetic energy is also in terms of moment of inertia we can explain. Like kinetic energy of any moving body we write as half m into v square. And if it is made up of number of particles, then you can write m1 plus m2 plus m3 v1 v2 all those things. But in short, I am showing here m square or m. V we can write as r omega whole square. Okay, and this r is nothing but the radius vector, position vector. Since we have discussed v is r omega, so that we can write this as half m into r square into omega square. Mr square is nothing but moment of inertia. Hence, the kinetic energy we can write in terms of half I omega square. The kinetic energy of rotating a body it is. This is kinetic energy of linear motion. The kinetic energy of the body showing linear motion. Kinetic energy of the body showing rotational motion in terms of moment of inertia. Kinetic energy equals to half I omega square. Of course, we can explain in detail like m1 v1 square half m2 v2 square so on. So that is minimized as m, where m is nothing but m1 into m3, r is nothing but v1 v2 v3 we have taken as r omega, since we know that relation between linear and angular velocity v is equals to r omega. Based on that, we have derived kinetic energy of rotating body, which is half I omega square. Okay, even with respect to the same, we can define the same as angular momentum also. Okay, that we will discuss in the next class.